is Annika Heckel from the University of Munich, and she will tell us about the non-concentration of the chromatic number. Please, Annika.
Yes, thank you for the invitation and the opportunity to speak here. Yeah, so this talk is about the concentration of the chromatic number of random graphs, or actually mostly about when it's not very tightly concentrated. So let me start by reviewing some background on graph colorings. So first of all, what is a coloring? So the setup is we have a graph. And we want to give a color to every vertex so that neighbors are always colored differently, like in this coloring. So whenever we have an edge, the endpoints get different colors. And the question is now, how many colors do we need to be able to do this? And that's the chromatic number, which we denote by chi. Okay, now by a random graph, I just mean the standard Erdős-Rényi random graph where we have n vertices and include every edge with probability p. And the question of the chromatic number of GMP has been around almost as long as GMP has been around. So it was already raised in the foundational papers by Erdős and Rényi. And so there are lots and lots of papers on this topic. And they, so these papers can usually be classed as into, or put into one of these two categories. So there are papers that tell us something about the value of the chromatic number. Usually these are upper and lower bounds. Now the chromatic number is of course a random variable. So by this I mean upper and lower bounds that hold with high probability, meaning with probability tending to 1. The other main kind of direction of research is, well, how much does the chromatic number vary? What can we say about the variance? Or what's the length of the shortest interval that contains the chromatic number? Again, with probability tending to 1. And as you might imagine from the theme of this workshop, this is the direction I'm going to focus on in this talk. But let me briefly say a few things about the value of the chromatic number. So much of the early focus regarding the chromatic number was in the random graph G and 1/2. So this is a very dense graph with lots and lots of edges. So one reason why people are interested in this graph is that it's the uniform distribution on all graphs on n vertices. Okay, and so the chromatic number, computationally, it can be very hard to work out the chromatic number of a given graph. So it takes a long time to compute. But Bolobas showed in 87 that in fact almost all graphs have asymptotically chromatic number, well, roughly n over log n. So it was known that this is not as a lower bound. This is not very hard, but Bolobas proved the missing upper bound in 87. So this is a very well-known result, and it was extended by Wuczak to almost all p. Now for our kind of favorite random graph G and 1/2, it was sharpened by various people over the years. And the best bounds for G and 1/2 that we have for the chromatic number is, well, this expression here. So this is an upper and a lower bound, and both hold with probability tending to 1. And the reason I'm writing out this bound, or this explicit result on the value of the chromatic number, is that later on I'm going to need it to say something about, or actually to prove non-concentration. So yeah, let's get to concentration. This last result, of course, is already a weak concentration type result. It gives us an explicit interval of length little o of n over log n squared, which contains the chromatic number with probability tending to 1. but that's, yeah, it's sort of really weak. And if we don't actually have to be explicit about the interval, so if we don't have to specify the interval, we can do a lot better than that. So the starting point for concentration type results for the chromatic number is the classic result by Chamy and Spencer. So also in 87, they showed that actually for any p, the chromatic number of GMP is contained in some interval of length about root of n. So for this, they used what is now a completely standard tool. They used martingale concentration inequalities combined with the vertex exposure martingale, where you sort of step by step, you reveal the edges of GMP and generate a martingale that way. So these days, if you wanted to show concentration of some graph parameter in GMP, this is part of our standard arsenal. This is the first thing you try, but they introduced this method in 87, and they used it to show that the chromatic number is concentrated on root n values. Now, in this general form, this result cannot be improved any further, because it's not so hard to show that if you let p tend to 1 at the right rate, so this means you have almost all edges in your graph and only a few of them are missing. In that case, you can more or less work out exactly what the chromatic number is, and you can see it's not concentrated. It's actually spread out over root of n values. So in this general form, this result can't be improved, but for specific p or for specific functions, p of n, it can be improved quite dramatically. So again, our favorite random graph GM1/2, well, if you work a little bit harder, you can get another log factor out. That was shown by Alon. But actually, if p tends to 0 quickly enough, so if p is less than 1 over root of n, then actually it turns out the chromatic number of GMP is 2-point concentrated. So this was shown by Alon and Kirilevich, building on the earlier work of Wuchak. So this is very, very strong concentration. I mean,
may I ask a question? What is 2-point concentration?
Oh, I mean, there are 2 consecutive values, and with high probability, the chromatic number takes one of these 2 values.
Wow, okay.
So it's an interval of length 2 that contains the chromatic number. So yeah, the chromatic number here is basically deterministic, because I'm saying 2-point concentration, but actually for most n it's 1-point concentration. Yeah, so this is a very, very, very sharp concentration. Now, all of these results so far, it's kind of a feature of these martingale concentration type results. None of them tell you anything about what these intervals are, or down here, what these 2 integers are. We just know they exist, and the chromatic number is contained in them with high probability. So for some p, the 2 values, or in this case 3 values, at most 3 values were worked out explicitly. So Akliopoulos and Noah, there's a well-known paper by them where they worked out what 2 explicit values the chromatic number takes in the case p is a constant over n. And that was extended up to n to the -3/4. But they lose a bit of sharpness. They can only specify 3 explicit consecutive values. Okay, so in the next picture, I'm just going to do a review of what we know. Okay, so the value we know kind of approximately pretty much everywhere that we're interested in. So this is an asymptotic result, the Bolobash result from 87, and then the generalization by Wuchak. We also have a general upper bound on concentration by Chamy and Spencer. And as I said, it can be sharpened almost maximally for p less than 1 over root n. And we also know what the values are for even smaller p. And so the range I'm going to focus on is in this talk is, well, the range where p is constant, or essentially anything in this gap here. So we don't really know what's going on here regarding concentration so far. In view of some very sharp results showing concentration of the chromatic number, starting in the late 80s, Bolobash and Erdős started asking the opposite question. So we know some cases where the chromatic number is very, very sharply concentrated, but do we know if that's always the case, or are there any non-trivial non-concentration results? So I've already told you if p tends to 1 at the right rate, it's kind of easy to show that you can't do better than root n. But are there any non-trivial cases where we know this? So the earliest reference to this in print I could find was from 92. So there Erdős focused on the random graph g and 1/2 and asked, well, can we show that at least for this dense random graph g and 1/2, can we show it's not, the chromatic number of that graph is not concentrated on a constant number of values? And if you recall what the best upper bound is, the best upper bound on concentration here is root n over log n. So this does not seem like the most ambitious question, but still it remained open for a long time. I think essentially because while we have tools to show something is concentrated, we don't really have a lot of tools to show something is not concentrated, other than in special cases where we can just work out the entire distribution. So Bolobash highlighted the question again in 2004, where he asked for any non-trivial examples of non-concentration and noted that he would be happy to see even the weakest results claiming a lack of concentration. Okay, so the main result of this talk is this. So the result is that the chromatic number of g and 1/2 is not contained with high probability in any sequence of intervals of length n to the 1/2 minus epsilon for any constant epsilon. So this result is joint work with Oliver Reardon, and we're currently writing up the paper. I'm very much hoping that this is not 2020 plus, but that this is 2020. I'm quite optimistic about this. Now, last year, this paper is on arXiv if you want to look at it. I had this up to n to the 1/4, and now it's n to the 1/2, which is significant because this matches the exponent in the best upper bound that we have by Alon. So up to this little epsilon, or little o1 if we want. This result is basically sharp. Okay. Now, I should give you a word of caution about this result. The order of quantifiers matters. So what we don't show is that for every n, the chromatic number is spread out over root n values. And actually, we don't believe that is true. So at the end of the talk, I will show you a conjecture what we think the right answer is for every n, and we think it depends on n. But what we show is that there are some values n where the chromatic number is not contained in an interval of length n to the 1/2 minus epsilon. And it's a feature of the method that we don't know what these n are. So we can only say there are some n, we don't know what they are. We don't know if it's true for n equals 1,000,000 or not. Okay, so so that's the plan. I want to talk about the proof of this result for a bit, and then at the end, show you what our conjecture is on what the truth is. Okay, let me first start by trying to convince you why you should believe this theorem is true. Okay, for this I need to talk about independent sets for a bit. Okay, so an independent set in a graph is just a vertex set without any edges between them. So a set like this, like I've drawn here. And the independence number of a graph, which we denote by alpha, is just the size of the largest independent vertex set. Now, independent sets are kind of much more local than the chromatic number, where you have to look at every vertex, and that makes them a lot easier to study in random graphs. So for our GN1/2, again, we basically know what the independence number is. The independence number of GN1/2 is basically exactly given by some function, alpha 0, which you don't have to remember, but it's some function of order log n. And if you round it down to the nearest integer below it, you basically get the independence number with high probability of GN1/2. Now there's sort of some annoying things can happen if this function alpha 0 gets close to an integer. So there's this little O1 term where if alpha 0 is close to an integer, the independence number of GN1/2 might take one of two values. But most of the time, when alpha 0 is far away from any integers, we know exactly what the independence number of GN1/2 is. Okay, and we know even more about this. So if we count the number of maximum independent sets, so independent sets of size alpha, because they are so small, they are of logarithmic size, they appear basically independently in GN1/2. So in particular, you can use Stein's method to show that well, the number of independent sets of size alpha is roughly Poisson distributed. Well, with the right mean. Now, what's the mean? The expected number of independent alpha sets, you can write it as some power of n, and what the exponent is actually depends on n. So there are values of n where this exponent is close to 0, and there are values where it's close to 1. And if you plot it, the exponent, it kind of looks like this. So this is a log scale, because then actually it goes up in a straight line like this. So yeah, for some alpha, the expected number of independent sets of size alpha starts out as close to 1. And then as you increase n, the expected number of alpha sets increases until you have about n alpha sets. And then at that point, alpha plus 1 sets start appearing, independent alpha plus 1 sets. So here, actually, the independence number jumps up by 1, and this exponent drops down to 0 again, because now you expect roughly 1 alpha plus 1 set, and then the same thing happens again until the independence number increases again. Okay, so that's the plot of the exponent of the mean of the number of maximum independent sets. Okay, where am I going with this? Now we know the number of alpha sets is Poisson distributed with this mean. And we know that a Poisson random variable is not very sharply concentrated. It varies by about n to the, well, root of the mean, n to the rho over 2. And if we pick some n where the expected number of alpha sets is kind of close to n, so if we pick an n that's kind of here, this means that the number of alpha sets should vary by, well, about root of n, about its mean. Okay, so there are some n where the number of alpha sets is not very sharply concentrated. Now that's good, but what does it have to do with our problem? So what do independent sets have to do with colorings? Well, if you think back to the definition of a coloring, so we wanted to color the vertices so that neighboring vertices are colored differently. Well, that just means that every color class is independent. So all the vertices of the same color don't have any edges between them, because the endpoint of an edge can't have the same color. So every color class is an independent set. And just from this easy observation, you get a lower bound for the chromatic number for any graph, not just a random graph. So the chromatic number of any graph is at least n, the number of vertices, over the independence number, because no color class can be larger than alpha of G. Okay, so in a random graph, this trivial lower bound is actually fairly close to the truth. So if you think back to one of the first slides where I was talking about the value of the chromatic number, actually, if you rewrite this, plugging in this definition of the function alpha 0, you get that the chromatic number of Gn1/2 is basically, it's roughly n over alpha 0 minus some constant. So that means we can color Gn1/2 so that the average color class size is only a constant below the maximum any color class may possibly be. Okay, and even more is true. So intuitively, it should be the case that the optimal coloring, the coloring that uses the least colors of Gn1/2, contains all or almost all of the alpha sets as color classes. So the reason behind this intuition is these types of colorings, they maximize the expectation. So we think they should be the ones that appear first in Gn1/2. And if that's true, and the number of available alpha sets varies by almost root n, then it should be true that the overall number of colors that you end up with should also vary at least as much as that, because you have to take in all the alpha sets, and the number of available alpha sets varies by almost root of n. Okay, so yeah. So if you think back to this picture that I showed you on what the standard deviation of the number of alpha sets is, our conjecture is that the chromatic number is not concentrated on fewer than, well, roughly this many values. You might have noticed I snuck a log factor in here. This is perhaps not completely obvious why there's a log factor. So the reason is if you have, say, t fewer alpha sets, then you have t times alpha vertices left over, and you have to color them with color classes which are, well, of size alpha minus 1 or smaller. And you can always put these leftover vertices into, you can always group them into color classes of logarithmic size, into much smaller ones. So you can salvage a log factor, but you shouldn't be able to do more than that. Okay, but enough about this. If you don't understand the log factor, that's fine. Yeah, but roughly the chromatic number should not be more concentrated than about the standard deviation of the number of alpha sets. And actually, our more general theorem is showing essentially this conjecture with a caveat. So we show that if S and Tn is some sequence of intervals which contains the chromatic number with high probability, then essentially for every n, there's some n star nearby, so that this conjecture is true. And this is, this is a feature of the method. We can never show for any specific n that this conjecture is true. We can only show, okay, for every n, there must be an n star nearby. It could be n, it could be another integer nearby, so that this lower bound holds, so that the length of the interval Tn star minus Sn star is at least, well, this lower bound. Okay, although we think, of course, it's true everywhere, but this is what we're showing. Okay. Now, if you have this intuition about the chromatic number and the maximum independent sets, What might you try to do about it? So one thing I tried for a long time was to take GN1/2 and to condition it on some typical number of alpha sets. So I put in kind of all the alpha sets and conditioned on these being the alpha sets. And then I wanted to compare it to another instance of GN1/2, but this time conditioned on a different, still typical number of alpha sets, which is a standard deviation away from the original one. And I wanted to show that if you put in all these R extra alpha sets, then the chromatic number goes down by a corresponding amount. Or conversely, if I have a coloring and I take out some alpha sets, then this increases the chromatic number by a corresponding amount.
Annika, we got a question on the Q&A, if you'd like to answer. CRS asked the following question. Can you see the questions?
Sorry,
I can let me.
Oh, so yes, now I can. Does this mean chi is not concentrated on infinitely many values of n? Well, I mean, for any particular n, everything is finite. I'm not sure. Now I know what you mean. Okay, does this mean chi is not concentrated? Yes. Yes, okay. There are infinitely many values n where the chromatic number is not concentrated on fewer than n to the 1/2 minus epsilon values. Because for every n, there's some n star nearby where it's the case. But yeah, we don't know, we don't have anything for all n. I hope this answers the question. If not, follow it up. Otherwise, I'll continue. Okay. Right. So, so the hope was if you put in some more alpha sets or remove some alpha sets, the chromatic number changes by a corresponding amount. I wasn't successful in doing this. So the problem is, if I have a coloring and I remove some alpha sets, there might just be a different coloring which doesn't use these alpha sets and still comes out at the same number of colors. So there was no way for me to ensure that the optimal coloring even uses the alpha sets. So this is why this first attempt failed. So what did work eventually, or one of the main ingredients of how to make the proof work is, well, we're not looking at GN1/2 for just one n, we're comparing GN1/2 for different n. Okay, so the picture looks similar to what was on the previous slide. What I want at the end, what is going to be useful for us is sort of a GN1/2 nestled within or embedded within a bigger GN prime 1/2. So n prime is slightly bigger than n. And I want the difference of these two graphs to consist entirely of alpha sets. And the reason I want this is then I can compare the chromatic numbers of these graphs, because then I know the chromatic number of the outer random graph is at most the chromatic number of the inner random graph plus R, because I can add all these sets as their own color classes. So for the moment, maybe you'll believe me, this is a nice gadget to have for the proof, even if you don't know where I'm going with this yet. So how would I construct this gadget? Well, what I'm doing, or what Oliver and I are doing, is just, well, we do the most straightforward thing imaginable. So the non-straightforward thing is showing that it works. We just plant our alpha sets randomly, and then include every other edge. So we say these are independent sets, so they don't have any edges. And then every other edge is there independently with probability 1/2. Now, what we have here, outside of these random alpha sets, is just a normal GN1/2, so that's fine. And what we want to show is that the outer thing, where we've planted these R random alpha sets, is sufficiently similar to a Gn prime 1/2. So it's not exactly a Gn prime 1/2 because we have planted the alpha sets, but the idea is if we don't plant too many of them, hopefully it's still going to be fine and basically indistinguishable from a normal Gn prime 1/2. Now to show this, it's actually cleaner to look at the effect of just planting a single alpha set. So this is what we call the planted model. So here we just plant single independent alpha sets uniformly at random from all sets of size alpha. And everything else is just a normal Gn prime 1/2. And the key lemma is that the total variation distance of the planted model and the normal Gn 1/2 is of order 1/√μ, where μ is the expected number of alpha sets. And so this means we can couple Gn 1/2 and the planted model so that they agree with quite high probability, probability 1 minus, well, this bound on the total variation distance. Okay, now, yeah, I think I have time actually to prove this lemma because the proof actually fits on one slide. So if you want, you can stop paying attention for this and then start paying attention again at the end of this slide. But I think the proof is actually quite nice because it's so short. So basically we can work this out explicitly. So the total variation distance for a discrete random variable, you can just write it like this. It is 1/2 times the sum overall values the discrete random variable may take. Now, random variable in this case is the random graph model. So we sum overall graphs on n vertices, and we subtract the probability that the planted model comes out as exactly this specific graph on n vertices, and the probability that the normal Gn 1/2 comes out as exactly one particular graph G. Now, and we can write these probabilities. So let's start with this one, which hopefully we all know. The probability that Gn 1/2 comes out as any specific graph is the same. It's the uniform distribution on all n vertex graphs. So it's 1/2 to the n choose 2, the number of possible edges. And now here, what's the probability that our planted model comes out as a specific graph? Well, first of all, our planted alpha set has to come out as one of the alpha sets in G. So there are x alpha of G choices for this, divided by n choose alpha, number of all choices. And then all the remaining edges have to come out exactly right. So either be there or not be there. Okay, good. And now we just need to rearrange these terms. So we draw out 1/2 to the n choose 2. And I want to write, in the denominator, I want to write the expected number of alpha sets. So that's n choose alpha 1/2 to the alpha choose 2. That's just the expected number of independent sets of size alpha. Okay, and what I'm left here with is mod x alpha of G minus, again, expected number of alpha sets. Okay, and here we have a sum overall n vertex graphs. And the weights here are the weights these graphs get in Gn 1/2. So this is actually just an expectation. Oh, I'm missing a factor 1/2 here. But it's 1/2 expected number of, well, expected deviation of x alpha from its mean divided by its mean. Okay, and now we can just use that. We know that x alpha is Poisson distributed. So we know it only, I mean, we know the deviation is of order root mu, and so we divide by mu, we get order 1/√mu. Actually, we don't need the Poisson approximation for this. It's enough to show that the variance is small enough, which is not so hard. Okay, so as promised, this is the proof of the lemma. So if you've stopped paying attention, you can now start paying attention again. Okay, so we know the total variation distance if we plant a single alpha set. Then the total variation distance to just the normal GN1/2 is of order 1/√μ, where mu is the expected number of alpha sets. And now I hope from this it's plausible that if we plant, well, little o of √μ of these alpha sets, then the overall total variation distance after repeating this little o of √μ times is little o of 1. Okay, so if R, the number of planted alpha sets, is less than √μ, this outer random graph G prime is indistinguishable basically from a GN prime 1/2. We can couple GN prime 1/2 and this planted model to agree with probability tending to 1. Okay, so overall we've constructed a coupling of GN1/2 and GN prime 1/2 so that the chromatic number of GN prime 1/2 is at most the chromatic number of GN1/2 plus R. Because whenever we have a coloring of the inner random graph, we can add each of these sets as their own color class and get the chromatic number, or get a coloring of the whole graph. Okay, so that's the first main component that we need for the proof. Okay, so that's the first ingredient. So we need a coupling of Gn and Gn prime, n is slightly larger, so that the chromatic number doesn't increase too much. The point of this coupling is, if we now assume we have intervals for every n that contain the chromatic number, and we have this coupling, then in particular we know that the intervals are at most r, the distance between them is at most r. Because if we have some value, so if we take some instance of GN1/2, which the chromatic number lands in here, and we couple it, or we take the coupled instance of Gn prime 1/2, the chromatic number is in here, and this is at most what we get here plus R. So the difference here can be at most R. Okay, so that's the first ingredient. Now the second ingredient that we need is a weak concentration result. So the other thing we need is an estimate for the chromatic number, which we call f of n, which holds up to some error term. And we need this estimate to increase sufficiently quickly. We need it to increase faster than, so we need the slope to be more than 1/alpha. On the next slide, I can explain why we need it to be more than 1/alpha. Now, luckily, this ingredient we already have. So if you think back to the, I think, second slide of this talk, or maybe third, there are the known bounds for the chromatic number of GN1/2. So we had this expression which holds up to some error term. So, and if we plug this in, this as f of n, and this of the error as the error term, and if you take the derivative of this, it has this property with an appropriate delta. Okay, so okay, what do we do with this now that we have these ingredients in place? So the picture looks like this. So this is the estimate for the chromatic number, the explicit estimate, which holds up to some error bounds. And we know the slope of this estimate is bigger than 1/alpha. And then we assume we have some intervals that contain the chromatic number with high probability. And we know from our coupling that if we go from n to n plus alpha times r, the next interval for that n, it moves up by at most r. So that the difference here between the intervals is at most r. So the slope between the intervals is at most 1/alpha, because you go to the right by alpha times r, you go up by r. And so now what happens is if all the intervals were very, very short, this would lead to a contradiction very soon. So if you kind of go from one interval to the next, and always the interval itself is very short, and then the slope is also less than 1 over alpha, then quite soon you would get out of this range that we know the chromatic number has to be in. So then here we'd have the contradiction. So here the chromatic number would have to be in this interval, and then also here. Okay, so this is how from those two ingredients you get a contradiction. And if you plug in, so you know there has to be at least one interval, but you don't know which one it is. You just know if they are all short, you get a contradiction, so one of them has to be long. Okay, and if you plug in all the numbers, what you come out at serendipitously is exactly what you need. So it's the lower bound from our conjecture, which of course is not a coincidence. It comes out because very likely the conjecture is true. Okay. Okay, so as promised, here's what we think the true concentration and behavior of the chromatic number is, because we've now only shown that there are some n, or indeed infinitely many n, where the chromatic number is spread out over more than n to the 1/2 minus epsilon values. But we haven't got anything for all n. I already told you about the conjecture of a lower bound for the concentration that comes from the count of alpha sets. Now there's also a different lower bound that's kind of similar but slightly trickier to understand, that comes from the count of alpha minus 1 sets. And it turns out that if you ban those two color class sizes, so if you only look at colorings that don't have these two, that don't have color classes of maximum or maximum minus 1 size, then the number of colors that you need is actually very sharply concentrated. So this is a paper I'm currently writing up with Kostas Panayiotou from LMU Munich. Again, I'm hoping this is 20, not 20 plus. But here I'm not as sure as with the other one. So we're using the second moment method, or a very complicated application of the second moment method, to show that what we call the alpha minus 2 bounded chromatic number of GM1/2 is actually 2-point concentrated. So this is, again, maximum concentration. It's essentially deterministic once we exclude the alpha and alpha minus 1 sets as color classes. Now, from this work and also recent work by Bolobash, Morris, Reardon, and Smith, there's, well, recently a conjecture emerged on what the true concentration interval length might be. So this is the lower bound I talked about earlier, which comes from the number of alpha sets. So this goes from n to the 0 up to n to the 1. I didn't label this axis, so this is the exponent of the concentration interval length. So n to the 1/2 here, and n to the 1/4, and so on. Now, the lower bound coming from the alpha minus 1 sets, which is slightly trickier to understand, kind of goes the other way. So this is the green thing. And the conjecture, which we call the zigzag conjecture, is that basically this is where all the non-concentration of the chromatic number comes from. So we all think the true behavior is that the concentration interval length kind of zigzags up and down between n to the 1/4 and n to the 1/2. Okay. Right. Yeah, so let me finish with some open questions. So the big open question, of course, is can you verify this conjecture? Yeah, I phrased it more carefully here. Is it the case that the correct concentration interval length zigzags between n to the 1/4 and n to the 1/2? Or if not, what does it do? Another big question that is left open is, well, can we say something about every n? So it's a feature of our method which doesn't seem to be, I don't think it can be changed. So our method only finds some n star near every n where the chromatic number is not concentrated. So it would be nice to have something that's true for every n. So as of now, we can't exclude the possibility that the chromatic number is not concentrated on some n, on some sparse subsequence, and then 1 point concentrated everywhere else, which is of course absurd, but as of now, the method doesn't really exclude that possibility. So next up, if we go to the very edges of the conjecture, so we have an upper bound for the concentration interval length, which is root n over log n. Now our lower bound is of the form n to the 1/2 minus little o1, where the function little o1 tends to 0 kind of slowly. It would be nice to close the gap between these two expressions. Now we think we might be able to push this lower bound to root of n over log n to the 5. That depends on some results I'm currently writing up with Kostas Panayiotou. Okay, so this would be then only within a log factor of each other. Yeah, and finally, I was talking about g n 1/2 the entire time. I'm pretty sure the proof also works for other constant p. But coming from below up to n to the minus 1/2, we have very sharp concentrations. So it would be very interesting to know, where these two regimes meet. So until what point do we have non-concentration going down until we meet this very, very sharp regime? Right. Thank you for your attention.
Thank you very much for a great talk. Very clear. Are there any questions to the speaker?
So I was just curious in regards to the second question that you listed. Is there
Yes.
no conclusion you can get from your theorem about every n? So you can prove it for that near each n you have some n star where you have everything perfect, essentially. Is there no conclusion at all you can get for every n?
Nothing whatsoever.
Like,
well, I mean, we know on average the concentration interval length is the lower bound that it's supposed to be around n, but at any specific n, it could be 1 point concentrated. So.
And another question is, so you don't think that there could be some feature of, I don't know, number theoretic features that some specific n will actually, give you some completely crazy picture there that indeed it will fail? You think it should be generic?
Sorry, I'm not sure I understood the question.
Never mind.
I think the question was, if there are some specific number theoretic reasons for some integers, and except for this rounding of log n, this alpha, is there some other number theoretic reasons for having some other effect in addition to this zigzag?
Well, we think the rounding of alpha 0 is the only thing that influences the behavior. At least in the first order. I don't know what goes on with the lower order terms. Yeah.
So can
I don't know of any number theoretic reasons why. Yeah.
Could I clarify something about the zigzag conjecture?
Sure.
So if you could go back to the slide, sorry.
Yes. Yeah.
So you said here there's a lower bound for alpha sets and a lower bound from alpha minus 1 sets. So does this? You're not saying you actually have a lower bound?
No. All of the, I mean, both of these are conjectures. This one we have verified for some n, where we don't know which ones they are.
And so should I interpret this lower bound as being, this is the sort of lower bound that you would get knowing what you know about the anti-concentration of the number of alpha minus 1 sets?
Yes, so this
Extrapolating
is,
from
I mean, yes, the number of alpha minus 1 sets also, we know how much it varies. You can also do a Poisson distribution, Poisson approximation on them. And this is kind of what you get when you kind of optimize your coloring profiles so that the expectation is maximized, and you condition on the number of alpha minus 1 sets that are available. This is kind of the variation you get out of that.
I see. Okay, thanks.
More questions? Okay, so let me thank Annika again, and we reconvene at 11:30 Pacific time, which is in 35 minutes.